This video is on inverse matrices, and we're going to prove what the inverse matrix of a 2 by 2 matrix is. We've looked at the other operations, addition, subtraction and multiplication. The question is there a division operator? So if we had this equation here, these two simultaneous equations, and we wrote them in matrix form here, so I've got a matrix times my x vector equals some constant vector, yeah? Well, what would we do in a normal equation? We'd do divide by, wouldn't we? We divide by m and we get x equals p divided by m. But it's not at all obvious what what division is in matrices. What we might actually want to do is think of it the other way around, is that division is actually the inverse of multiplication. And there are other ways of thinking about it. So if I do 2 times by 5 and then I divide by 5, I get back to 2, don't I? Or I could do 2 times 5 and then times a fifth. And effectively the fifth there will give us like an inverse multiplication, wouldn't it, if we use the reciprocal? So what we're going to actually focus on, because it proves it is possible, is that we can have an inverse matrix that does the opposite of what our original matrix did. A bit like 1/5, multiplying by 1/5 does the opposite of multiplying by 5, yeah? And that's what we're going to do. So let's prove that that works using a simple example. Okay, here's two simultaneous equations, two unknowns, x and y, yeah? So we can write it as equation form, or we could rewrite it here on the right hand side in matrix form, where we've taken our coefficients out, we've put our x's together into a vector. That's what we really want to know, is what this vector is, and we've put the constants together, 9, the 5, into another vector there, yeah? Now, if I was just solving this with simultaneous equations by elimination, what would I do? I'm going to eliminate the y values here. Well, I do that by taking the first equation and multiplying it by 5, which comes from there, so I get 10y there. And then I take the second equation and I multiply it by 2. And I get the 10y there, and then I take one away from the other, and I've got 0y left, so I've eliminated the y, and I've got 7x equals 35, therefore x equals 5, yeah? And if I carried on, I would then substitute that back in the x value into equation 1, and 3 times 5 is 15, I've got 2y there, I've got 9, so 2y is minus 6, and y is minus 3. Okay, straightforward piece of solving simultaneous through elimination. I'm going to generalize that now, because that will help us find out what our inverse matrix is. So rather than having 3, 2, 4 and 5 here, I've called them A, B, C and D. And then for my two constants, 9 and 5, I've called those P and Q. So effectively I've got constants vector there, haven't I, P and Q, and that's going to become important because we're going to use that later. Okay, so what we do, as we did before, we're going to eliminate the y term. So I take the first equation and multiply it by d, that's the 5, yeah, and so I get b dy there. And in the second equation I multiply by b, that's the 2 here, and I've got b dy there, and I cancel them, effectively take one equation away from the other and they disappear, don't they, cancel out. But what am I left with in the first, with the x's? Well, I'm actually left with this coefficient out the front. I've got AD minus CB there. I've rewritten that as BC because we're going to use a term for this, because it's going to be, we're going to call this our determinant, because it's going to appear all the time, this little bracket. Because if I take my next step to find x, well, I want to divide by that in the same way I divided by the 7. Here I'm going to divide by the AD minus BC, and what have I got? I've got an equation for x, and the denominator is ADBC, that's the determinant, AD minus BC, and you can see that all of those terms come from the left hand side, don't they? They all come from this side of the equation, yeah? They're all going to be in the matrix. That's going to be inside our matrix. So that's the denominator. The numerator is a combination of P's and Q's and the coefficients D and B. but we've now found out what x is. If we then substituted that x equation into back into equation 1, then we rearrange it, so I've just got my by, because I'm trying to find y now, aren't I? Like I had 2y on its own, now I've got by on its own once I've subtracted this term from both sides. I want to get it over a single denominator, so I'm going to multiply that up, and I get 4 terms now when I expand the brackets. 1, 2, 3, 4 here, 1, 2, 3, 4. And actually these two terms, PAD and APD, are the same, aren't they? So they cancel out. So I'm now just left with 2 terms on the top, and actually we can see here that both of these terms have got b in them, so b is a factor, so I can bring b out the front, put the rest in a bracket. So this is my equivalent of 2y equals minus 6. And what am I going to do next? So well, I'd have divided by 2, so I'm going to divide by the b, and of course the b's on both sides, so that effectively cancels out. So I've now got, my solution was y equals minus 3, and now I've got a more general expression there for y. Okay, let's put both of those together, side by one above the other, so we can see for the x and y. So x was 5, y is minus 3. And if I look at these two here, these two more general solutions for x and y, well, they've both got the same denominator, haven't they? AD minus BC, but they've got different numerators. So if I rewrote that in vector form, by just effectively doing this, I get down to here, and I'm going to take the AD minus BC out the front of my vector because it's a constant. Hence my interest in having this thing called a determinant and treating it as being like some sort of constant. There we go. And I put the other parts here, the numerators going inside my vector, aren't they? As the x term, so that's the x term and that's the y term. Now you can see where we started from. We had p and q as a vector in our original equation. So I'm going to put the p and q out the back, and I'm going to create a matrix which, if I multiply by that p and q, will give me these terms up here. And that's pretty straightforward to do, because here I've got PD, and so when I'm doing my multiplication here, I need to have a d coefficient there to multiply by the p. So that term there is going to be that term there is going to be a d, and for my here I've got a minus qb, so this coefficient this in here must be a minus b, mustn't it? And then on the lower line I need to get to PC minus PC and minus PC plus AQ. So what am I going to multiply my P by? I'm going to multiply by minus C. What am I going to multiply my Q by? I'm going to multiply it by plus A. So what have I done there? I've created a matrix, haven't I? This purple matrix here. There we go. I've created something that, if I started with the equation we originally had, here it was, generalized, my matrix times my unknown vector equals a constant vector, yeah, which I could write as matrix times vector m times x equals p. What we've just done is effectively created a reverse of that equation, or an inverse of that equation, because now we've got the x on its own, we've got some matrix here, and then we're multiplying it by p. Well, that's really useful, isn't it? So what we're going to do with this here, well, we're going to call that the inverse matrix, yeah. So in this case, there we go, m, and we put, to show it's the inverse, we describe it as m, and where the power is, we put a little minus 1, yeah. Same way that if we had m squared, it would mean 2 lots of m, m times m rather. Here, m minus 1 is going to be the inverse matrix, yeah. And we have a standard algorithm now for calculating that matrix, yeah, that we just do our determinant out the front, 1 over it, and then we're going to swap over. If you have a look at this, we've swapped over our A and D here. There's our A and D, they've swapped over. And what's happened to the B and these two here? Well, they're the same, but the signs changed, yeah. So we've got a standard way of creating an inverse matrix. So there we go, just our little summary before, then we'll move on to the second video and describe it more. But if I have this matrix M, I can find the inverse matrix of it using this little algorithm here. And effectively what we're doing there is we're taking this initial equation, M times X equals P, and we are changing it, finding effectively the inverse equation by doing like the equivalent of a division or multiplying by a reciprocal. We effectively got find our x, because x is going to be our inverse function times our p, and this term m minus with a power m minus 1 is the inverse of m. And of course there is something that's important here, which is this only works, this method, if AD minus BC does not equal 0, because if it equals 0 we've got to divide by 0, and that gives us a real problem. So there we are, that's the first part of it. That's how we get our inverse matrix. In the second video we're going to go through using it and looking at it in some more detail.